Donc, si Yassine, après, tu me diras par WhatsApp, wesh, tout se passe bien côté YouTube. Ok, on va dire lancer, on verra.
واخد أكونت.
All right, I think we are live. So, hi everyone, and welcome for this new webinar session with our guest Walid Maouaki. To tell you a little story, actually, I met Walid in Indaba, the great Indaba conferences. So, as you know, there are like local Indaba conferences called Indaba X in each country, and there's the big one, the deep learning Indaba. That was actually it's an annual conference, and this year it was organized in Dakar. And I was lucky actually to be there in Dakar and to attend that conference. And I was also very happy to meet Walid because Walid actually was the winner of the best poster in Indaba X Morocco. So he did represent Morocco in the Deep Learning Indaba conference. And I've been to his presentation. It was a very nice presentation. I was very happy with how he presented his work. And of course, with MoroccoAI, we decided to invite him for this webinar. So we are very happy to have you here with us, dear Walid. And
Thank you very
yeah,
much.
I will start. Yeah, sure. I will start just by reading a short biography of you, and then I'll leave you the floor. So, Walid is a PhD student at Hassan II University in Casablanca, Morocco, specializing in quantum machine learning applications and security. His work spans the development of quantum algorithms for healthcare and cybersecurity, as well as securing these advanced systems. So he's an active contributor to the quantum computing community. He has presented his research at international conferences and mentored many members of the next generation of researchers and developers through hackathons and internship. He's passionate about inclusivity. He's dedicated to create supporting environment for students from diverse background. And looking ahead, he's eager to continue his research in quantum machine learning, focusing on addressing some of the field's most pressing challenges. We are very happy to have you with us, dear Walid, and I think the floor is yours. You can start sharing the screen.
Thank you very much. I appreciate it and very happy to meet you. And actually, in Daba, it was an amazing experience and memorable experience. And I met a lot of interesting and incredible people like you. So really happy and looking forward for Indaba 2025 and see you all there.
Inshallah.
Yeah, thank you
Inshallah.
very much. So I will share my screen. So just tell me if everything looks good.
So yeah, we're just waiting for can you go for screen?
Okay. All right.
Yes, perfect.
Okay, great. Yeah, so thank you very much for inviting me to present my work. Today I'm going to present you my work about applying quantum computing to the healthcare sector and how we can use quantum machine learning to enhance oncology problem and cancer diagnosis. So before that, I should present you with the fundamentals of quantum computing and the fundamental building blocks of this technology. Let's start first with superposition. So unlike classical bits, which could be either 0 or 1, qubits could be 0, 1, or both at the same time. Like having flipping a coin in the air until it lands, it's both heads and tails. So this is called the superposition property for qubits, and the whole quantum computers are based on these qubits. So qubits or quantum particles behave also like wave. So they have this property of interference like wave. So the case of constructive interference, we have when the phase of our waves, let me show you. Okay, so when the phase of the waves aligns, they amplify and result in a bigger amplitude wave. However, for the case of destructive interference, when the phase are out of phase, where the waves are out of phase, they cancel out. So we have like a line, which means that both waves got cancelled. So this property helps qubits amplify the probability of finding the correct solution. And another one is entanglements, where can qubits be interconnected and allowing their state to influence each other instantaneously. And finally, we have measurements. So measurements collapse the superposition states and enable us to extract information from the system for further analysis, like in machine learning, in quantum machine learning tasks. Like in the coin length, when the coin length, the measurement reveals the qubit states. So since the measurement is probabilistic, we require several measurements in order to extract reliable distribution of our results, ensuring that we have like a good data for analysis. So what is quantum machine learning? Quantum machine learning lies at the intersection between quantum computing and machine learning. So we first, on one hand, we take elements from quantum computing, such as entanglement, superposition, interference, and the concepts of Hilbert space. And on the other hand, we use elements from machine learning like inference, optimization, and hyperparameter tuning. And this combination creates quantum machine learning models, which are hybrid classical quantum approach, which could process quantum and classical data in a fundamentally new way. So the goal of quantum machine learning is to enhance data processing and analysis by applying what we know from quantum computing to machine learning in order to help solve problems that classical computers struggles with. So what is quantum neural network? So quantum neural network is one of the quantum machine learning models that is used for classification, and it has the potential to accelerate and increase the classification accuracy of large data sets. So to show you a little bit of the architecture of this quantum neural network. So the quantum neural network consists of several layers, classical layer and quantum layers. So this part is a classical layer, and this part is a quantum layer. So hence the name is hybrid quantum classical machine learning models. So in the part of classical parts, so we got our data, we process our data and structure it in order to be ready for quantum embedding or in the quantum layer. In this quantum embedding, we have this data which gonna parameterize our quantum gate in this circuit in order to transform the data into a quantum states. So after that, we operate on these quantum states via variational circuits, and this variational circuit has adjustable parameters that could change in order to change the quantum states. And yeah, the next step is measurement, as I said before, to collapse the state and extract useful information. And this information is fed into a layer for cost function, which help us evaluate the model performance. And via like an optimization loop, it's gonna help us adjust these parameters of the variational circuits in order to refine our model and converge toward the solution. Right, so to show you how these quantum models, quantum machine learning models work on real hardware. So in the case of variational circuits, so the variational circuit try to adjust the state or the rotation of qubits. As you can see here, the rotation of the qubits are all going to change the rotation in order to so this change of rotation is made by the optimization process. Like the optimizer give us feedback and adjusts the overall quantum system configuration. And this configuration is our solution to the problem. So when we measure this configuration, the cost function is minimized, and we get the classification or prediction task, whatever the task we want to do with our machine quantum machine learning model. So this image is a superconducting computer or quantum computer. So these kind of computers operate on low temperature in order to preserve the quantum states of our computer, of our system, which is necessary for doing quantum computation. Right, so now I'm going to show you how this quantum computing raise in healthcare. So like quantum computing witnesses a growing investment and partnership between tech companies in the healthcare institution and accelerating the integration of this quantum computing in the healthcare. So recently, like in 2021, like a partnership between IBM and Cleveland Clinic have been established in order to explore quantum computing in the field of clinical research, for instance, for doing drug discovery or for personalized treatments. So this is just one of the examples that shows the integration of quantum computing in the healthcare sector. And this trend is driven by better access to global health data and increasing power of classical and quantum approaches. So as the quantum technologies progress, it's paving the way for practical application in the healthcare. Right, so quantum computing and what kind of capabilities this quantum computing can bring to the sector and help us solve our problems. So one of the key like advantages of quantum computing is speed and accuracy. As I told you before, quantum computers can represent multiple states into like simultaneously, and this is called the superposition phenomena. Meanwhile, entanglements, which allow qubit communication, in order for qubits to collaborate and communicate with each other and collaborate towards conversion toward the solution. And so by evaluating many possibilities at once, quantum algorithms can explore the solution space more efficiently and thoroughly, and like which reduce the risk of missing the correct solution. And this also enables us parallel computation. Also, quantum computers are more energy efficient than classical computers, as they may have required fewer computational steps due to this parallelization computation, which gonna reduce the energy consumption. Finally, data security. Unlike classical cryptography, which they rely on the mathematical complexity for securing communication, quantum cryptography or quantum key distribution rely on the fundamental laws of physics to secure communication. So a common protocol called the BB84 protocol, which relies on the particle flights or photons to transmit information of data. And so whenever an eavesdropper try to intercept this communication, like the state of this photon change, and it immediately alerts both parties of this intrusion. Yeah, so what are the implication in the healthcare sector? There are a lot. One of which is drug discovery, where it's gonna reduce time and resources needed for drug discovery, and it helps us to do faster analysis of molecular structures. Also, it enhanced data processing in MRI and CT scans, which gonna accelerate diagnosis, and in the genomics analysis. So efficient analysis of large genomics data sets help us to do personalized medicine and efficient treatments. Finally, we need to protect patients' data. We can implement these quantum cryptography protocols to secure communication. All right, so what are the problems of cancer diagnosis? So there are a lot of challenges. First of all, oncology deals with analyzing vast amount of data and complex data sets, including genetic information, clinical data, and research studies. So traditional computers struggles with this kind of analysis and processing of data. Yeah, so also another problem is that every cancer case is unique and it requires personalized treatments, and this demand individual patient analysis, which could be resource intensive. Yeah, so also the process of developing new cancer drugs takes time and computational power to simulate molecular interactions. So it's gonna help in drug discovery and challenges, potentially with quantum computers. Also, finally, the early detection of cancer, which is crucial but challenging because it is hard due to the hidden early stages indicators. What about how quantum machine learning can help address these challenges in cancer diagnosis regarding this data processing and analysis? So first, quantum machine learning can analyze high-dimensional data to find patterns missed in the classical methods, and this enhances early cancer detection. Also, quantum machine learning explore and leverage this parallelism of computation, which gonna help rapidly process complex data sets for quicker diagnosis. Also, quantum machine learning enhance the accuracy of MRI and CT scans analysis as discussed before, which gonna lead to better identification of cancerous cells. Finally, quantum machine learning efficiently analyze genomic data, so supporting like the personalized diagnosis and more effective treatment plans. All right, so in our work, we use quantum support vector machine for prostate cancer detection. And to start with, I'm going to introduce you to support vector machine, specifically first the linear version of support vector machine. So what are support vector machine? These are set of supervised learning methods for classification, regressor, or even outlier detection. So the idea behind this linear support vector machine is to construct a hyperplan that best separate classes with a maximum margin. That is the maximum distance between data points of different classes. So in this example, we have two classes in green and blue. And this middle line is the hyperplan, the straight line, because we are dealing with linear data. So we only require a straight line to separate between different classes. And dashed line are the margins. So the wider the margins, the more our model is confident about classification, and the lower the generalization error in the classification. The objective of this linear support vector machine is to minimize this cost function subjected to some constraints. And these are the hyperplan's equations. Yeah, so the problem here is that in our real world data, we don't face linear data sets. We usually see non-linear data, specifically in healthcare. So for this, linear support vector machine can't handle such data. And yeah, so to solve this problem or adapt this support vector machine, we introduce the kernel trick. So this kernel trick allows support vector machine to operate in a higher dimensional space. So this is an example of nonlinear data, which where we can't like separate the data with a straight line. So the idea is to like map this original space using a feature map function into a new space called a higher dimensional space, where it is easy to create space between classes and help us to create a hyperplan, a linear hyperplan that can separate data sets more efficiently. So here the objective function now relies on the computation of the kernel matrix. So the kernel matrix represents the distance between data points from different classes. So the farther apart these points are, the easier to become to draw a linear hyperplane to separate them. So this equation shows how the kernel matrix is central for optimizing margins between classes. And why this is important? Because current classical computers find it very hard for large data set to compute this kernel matrix. To show you how the support vector machine, the key difference between support vector machine and quantum support vector machine is that at their respective approaches for mapping data from original space into a higher dimensional space and how they compute this kernel matrix. So let's go for the example. We have a data set, right? If we follow the paths of a classical one, we take this data set and we map it using a feature map function classically. And this feature map is going to map this data into a classical higher dimensional space. And after that, so this higher dimensional space allows us to separate the data and make it easy for us to draw a straight hyperplane. So the kernel matrix is computed by computing the inner product of this transformed data in this new space, and allow us to compute the kernel matrix of all the data sets. However, if we follow the quantum paths, so it is a little bit different, but serve for the same goal. So for here, we use quantum circuits in order to do this feature map. First, we need, so this data going to parameterize these quantum circuits in order to create a quantum state. So instead of using using these feature map functions in the classical part, we use quantum states in order to map this original data into a new space called the quantum Hilbert space. So this quantum Hilbert space have dimension of 2 to the power of n, where n is the number of qubits, which is exponentially larger than the classical space, which only n-dimensional. So this allows quantum support vector machine to handle much more complex data relationship. So the classical data is used to the kernel is computed using the inner products between these quantum states instead of this feature map, right? All right, so I'm going to show you about the architecture we used in order to apply this quantum support vector machine for prostate cancer detection. So we start with MRI-based prostate images, and then we pre-process this data and structure it. So from visual features, we transform it into numerical features, capturing physical and geometrical properties. And so the key data set variables we extracted are two numeric variables and categorical variables. These categorical variables diagnosis help us give us the solution, which is cancerous or non-cancerous cell. So after this pre-processing, we feed these quantum variables, these classical variables, into quantum circuits, which is a quantum feature map. Then we compute the quantum kernel and feed it into the classical part of support vector machine, like the optimization part, which is still classical. And then we extract information or classification, either cancerous or non-cancerous. And the results are pretty interesting. So this like figures shows us the kernel matrix of both feature map. So the feature map using classical techniques, which is the RBF technique, and the feature map using quantum feature map, using quantum state to map this data into a higher dimensional quantum Hilbert space. So as you can see, so the diagonal here is the distance between the data set with itself. In the off diagonal, in the classical part, we see that there are a lot of high values that indicate that data are similar to each other in this new space that's been transformed to its data. And yeah, so as you can see in the quantum kernel, we have like a sparse matrix, which tells us that the data are well separated from each other in this quantum Hilbert space, which is pretty interesting and really help the optimization process of support vector machine to distinguish between data classes and output accurate results. So quantum support virtual machine leverage these quantum properties, which allow for richer exploration of the feature space, enhancing our understanding of complex correlation within the data. Right, so regarding the performance metrics, as you can see here, this line is for quantum support virtual machine, and the bottom one is for support virtual machine. As you can see, for accuracy, they both score the same score, which means that both model perform a generalized well for unseen data sets. However, for quantum support virtual machine in the sensitivity score 100%. So this is an improvement of process cancer detection by 7.14% over support vector machine. So with no false negatives. So this is crucial and critical for minimizing the misdiagnosis. Therefore, we can conclude that quantum feature mapping enhance classes separation, leading to stronger confidence in identifying positive cases. Also, for the F1 score, the quantum support vector machine outperformed a little bit support vector machine, which both tells us that both models have better overall balance between precision and sensitivity. However, if you can notice that in some other metrics, support vector machine outperform quantum support vector machine. So this is tells us that we can have a balanced approach between support vector machine and quantum support vector machine. So depending on the use case, both classical support vector machine and quantum support vector machine are valuable tools. And the choice should be guided by the specific metrics most important for the doctor and the clinical requirements. All right, for the conclusion, future direction should be expanding this quantum support vector machine analysis to a larger and more varied data sets, and exploring quantum support vector machine for potential diagnosis in various cancer and diseases. However, there are some limitations because quantum computers at the moment are still at their infancy. So there still be some work to do in the quantum hardware part in order to implement our quantum software or quantum machine learning models into it. And yeah, so also for our side, for quantum developers, we require that to develop quantum algorithms that are more tailored for these small quantum computers that we have access to it right now. All right, so this is the QR code for the paper we have showed the result from, and my email to contact me. And thank you very much for your attention, and any questions are appreciated.
Thank you very much, Walid. Very nice presentation. I myself, I'm not very familiar with the domain, but I learned a lot from your presentation. So yeah, sure, we got questions, and some of the questions are very general, some of them very specific. So let me do a mix of both, okay? If that's okay with you. So the first, some of the question were really very direct. For example, one question was how much time and energy do you gain compared to the classic algorithm when you move to quantum SVM, for example?
All right, so using this quantum algorithm, the exact number, I would say that since our models is efficient in processing the data, it makes the quantum model more efficient and make it easy for the quantum optimizer, for the classical optimizer, in order to classify the data. So for this sake, we require fewer steps in order to do this optimization step. So this will tell us that the problem of energy consumption is reduced, and also the time to do classification is reduced, since this quantum space is more efficient and can process the data more efficiently than the classical part.
All right. The second question, which was also very direct, is why working with SVMs? Is it for the compute constraints?
Okay, so okay, you mean these constraints used in the
I
yeah,
think
so
the
the
person
quantum,
is asking, I mean, why SVMs are not other machine learning techniques?
yes, we can use other quantum machine learning models in order to do this kind of processing. For instance, we can use quantum convolution and neural network. Yeah, so there are a lot of approaches. Why we use this quantum support vector machine? Because also support vector machine is widely used in this healthcare sector. And what about using quantum support vector machine in order to do to process data more efficiently and keep the optimization part for the classical part? Yeah.
Okay. One related question, which is also actually it's related to the question before that one. It is on the power consumption. Did you perform like some kind of power consumption analysis for your algorithms and compare them to the classical ones? Or do you know maybe
Mhm.
papers who did
Yeah.
that?
Yeah, so that's interesting question. Actually, in our simulations, we did not use the quantum hardware itself. We used only quantum simulation in these results. So we haven't done this analysis, energy consumption or time spent in this kind of um, processing. So we only showcases the advantages of quantum data processing of of our problem.
All right. Now I'll move to more general questions. So one question is on neural nets. So is it always quantum layers in a quantum neural net, or we can mix classic and quantum layers?
Yes, that's exactly. That's a very good question, and we could do this. Actually, this model is one of the models that we can use. We also there is another model called the convolutional neural network. So we can apply quantum circuits in order to pre-process the data, and then apply neural network, which are classical, and then we can mix both of them in order to complete this convolutional neural network model and do classification or any machine learning task,
And
specifically for images and
right.
imaging process.
Yeah, right. And one other person actually asks a very, I think, interesting question. So, I mean, practically, he said, practically, how do you, what is the difference between a layer, a classic layer and a quantum layer? I mean, in the code, what is exactly the difference?
Yeah, the difference is in the data processing. Yeah, so in this, if you can see, this is the quantum layer, right? So there are a lot of, in this architecture, there are two classical layers. So the first layer here, we use it for pre-processing the data and structure the data to make it ready for encoding into a quantum states. So, so in the part of quantum layer, we process the data using qubits. And for this, when we encode the data in the quantum circuits, we take the advantage of these quantum properties into our data, the superposition, entanglement, and interference stuff, in order to process the data more efficiently. Then we measure the data to extract information. And for that, we use a classical layer for optimizing the parameters of our qubits. So the parameter of qubits are their rotation with respect to their axis of rotation. So if you change the rotation of this qubit, you change the configuration of the whole system since they are all entangled. So yeah, so this gonna answer the question: what is the difference between classical and quantum? And we can make them work in tandem, as I answered in the previous question.
Okay. And yeah, and the next question, so you have shown binary classification problems. Have you worked on multi-class classification problems?
For this problem, we only have binary classification. I also worked on multi-class classification problem. However, if you use this kind of architecture, we're gonna fall in a problem called Barren plateau. So this Barren plateau are gonna always lead you to a local minima instead of global minima. And yeah, so the technique of using multi-class classification is also true in quantum neural network. We can use it with other architecture too. For instance, in the co-involutional neural network, the part of processing the data could be done with a quantum circuit, and this classification, multi-classification part is done with the classical part, with the neural networks. So we measure this 10, for instance, a 10 classes problem, we measure the 10 neurons at the end for output.
All right. So we do have other questions, but for the sake of time, we just select like three last questions, okay? So the first one is also very practical. What Python library do you recommend for quantum machine learning?
I would recommend Penny Lane to use like quantum machine learning models and learn about quantum machine. So also there is Qiskit. They are doing good work on this too. And what I've used in my work, if you told me, I will recommend you to use Penny Lane. Yeah, so
Okay, yeah,
short answer.
it's good that you mentioned Qiskit because there's another question related to it. The person said, did you attempt to use physical qubits to do the task, such as D-Wave, I'm not sure I pronounce well, or the IBM Qiskit?
Yeah, so in my problem is the problem, like the model of quantum support virtual machine is a gauge-based problem circuit, which can only be performed on the like gauge-based quantum hardware, like the superconducting quantum computers. Yeah, so I have used only the simulator for this sake, and I haven't used real hardware for that. So we are planning to do this and analyze the effect of quantum noise in our results, and if our results stand true for this kind of noise.
Okay, so yeah, for the sake of time, I'll just take a last question. I will be a
Sure.
little bit
Yeah.
selfish, so it's my question actually. So
Okay.
my question is very simple here. So we have, well, myself, I have always this idea that quantum machine learning is maybe, especially research, is probably just done in developing countries. Okay, so I would like to know what are the challenges of like doing quantum research in Morocco? And how do you, I mean, is it very hard? Is it okay? What are the limitations you have? Just like to clarify the idea for persons like me who do not know too much the field.
Yeah, so yeah, that's interesting question. Very good. So I would say that in Morocco or any like country that doesn't have a real hardware to work with, people tend always to use to go for the field of quantum softwares and develop quantum algorithms to solve problems for application or even securing these kind of softwares. However, if you want to do research on the real hardware, it is a little bit challenging because we don't have this access of physical quantum computers. To have this kind of access, you need to apply for internships abroad, and yeah, so there are a lot of competitive activity. So yeah, I would say you can always get in this quantum field, quantum computing. I have started even in my undergrad studies, so there are a lot of resources in the web internet, so you can always access this kind of tutorials, textbook on quantum computing and learn. And you should always stay in this. You don't just need to be to stay in this consumption, consuming part. You should also look forward to be a producer. So you're gonna find this gap between consumption and production in order to be useful in the research community.
Interesting. Thank you very much, Walid. So I still
You
see
see,
some questions, but maybe we leave them for the breakout session after
sure, yeah.
the end of the live stream, and you can ask directly to Walid your questions. And of course, Walid also showed his email, so do not hesitate to send him an email also if you have any other questions, especially if you see the live stream later. Okay, so I will just stop the live stream and we will move to